Hi everyone, welcome to Recitation 10. Our plan for today is mostly going to be the L'Hopital rule, and towards the end, a few exercises about antiderivatives. So I'm going to start by reminding you what the L'Hopital rule is, or are if you want to call them rules. So basically, when we are computing limits, there are certain forms which are called indeterminate forms. I have a list of all of them up here. Basically, which means that whenever you find limits like this, the answer could be really anything, and you have to do something to simplify the functions. And the L'Hopital rules help you with the first two, quotients of the form 0 over 0 or infinity over infinity. The other ones, you need to somehow modify them, simplify to transform into the first two. And what are the L'Hopital rules? Well, if you have two functions, f and g, differentiable, and such that the limit of f over g is of these forms, 0 over 0, infinity over infinity, then it's going to be the same as the limit that I'm calling L2 here with f prime over g prime. This is not the quotient rule. We're not applying a derivative to the quotient. We're not doing that. We're just applying primes to each one of the functions separately. And provided that this L2 exists, that's important. If you find a limit after applying the primes on f and g, then that's the same as the limit L1. And the symbol A, the location where the limit happens, that could be anything, a number, a one-sided limit like A plus or minus, or one of the symbols plus or minus infinity. So we're going to be doing many examples of this. Here's the first one. So the limit is x going to 1/2, and you have ln of 2x divided by x squared minus 4. So writing this very informally, if you try to plug in 1/2 into x, what are you going to get? Well, ln of 2 times 1/2 divided by 1/2 squared minus 1 over 4. 2 times 1/2 is 1 inside of the ln. ln of 1 is 0. And downstairs, 1/4 minus 1/4, it is also 0. So 0 over 0, that means you are allowed to apply L'Hopital. So I'm going to write a little LH here to indicate that we are now using L'Hopital. So we need to find the derivatives of both the numerator and denominator. The derivative of ln of 2x, it's not just 1 over 2x, you have to multiply that by 2. This is the chain rule, right? If you apply the derivative of the outer function ln, applied to the inner function 2x, you get this 1 over 2x. And then multiplied by the derivative of the inner function 2x, which is 2. So this is the derivative in the numerator. Denominator is easier, that's just 2x. X squared becomes 2x after you apply a derivative. So now we can simplify this. How do we do that? Well, the 2's in the numerator are going to cancel. That's just a 1 over x. So we have limit x going to 1/2 of 1 over x divided by 2x. So 1 over 2x squared. And what is this now? Well, this in this form, you are allowed to plug in 1/2 for x. 1 over 2 times 1/2 squared. So 1 over 1/2, that's the number 2. Yes, that's the answer to this limit. So most of the problems today are going to be this easy. Maybe a little bit longer than this, but the idea for L'Hopital is very easy. So here's the next one. Once again, if you try to plug in, let's see what happens. That should be your first thing to try always. X is going to pi over 4. That's 45 degree. If you want to think of this as angles, 45 degrees. Tangent is 1. And then cotangent is the inverse of tangent or reciprocal of tangent, so 1 over 1. Meanwhile, downstairs, you just have pi over 4 minus pi over 4. So this is 0 over 0, which means you can do L'Hopital. So let's do that. Well, now you just have to remember how derivatives work for the trig functions. Derivative of tangent is secant squared. And the derivative of cotangent, that would be minus cosecant squared. Just double checking my work. Minus cosecant squared. This is the one that I told you I never memorized. If you don't know how to find, if you don't remember the derivative of cotangent, you can either look it up or just remember that cotangent would be cosine over sine. So if you want the derivative of that, you can use a quotient rule, and this is what you're gonna get. Minus cosecant squared. And downstairs, the derivative of x is 1. The derivative of pi over 4 is 0. So you have your expression. It's not even a fraction anymore. If you write it in this form, it's just secant squared plus cosecant squared. And now those are continuous functions, both of these guys, which means you can just plug in pi over 4, they give you a value, and that value is the limit. So in this case, secant squared is 1 over cosine squared. So I'm plugging in pi over 4. And then cosecant squared, 1 over sine squared. Also of the angle pi over 4. Both of those are square root of 2 over 2. The sine and the cosine of 45 degrees. So now when you take the squares of those, 2 over 4 is 1 over 2. Each one of these fractions is equal to the number 2, giving you the answer of 4. So these were simple examples involving L'Hopital just once. We're going to see some more later where you have to apply L'Hopital again and again. Here's another one where when you start with, you don't see a fraction or quotient. This is a product between two functions. But what do you do? First, you try to plug in x equals 0 to see what's happening. So let's think about this. Sine of 3x is equal to 0. Sine of is going to 0 when x goes to 0. And then what is cosecant? Well, cosecant is 1 over sine. It's going to be either plus or minus infinity, depending on which side you're coming towards the number 0. So I'm going to write it like this, for example. If you're going to 0 from the right, then both sine and its reciprocal, cosecant, those are positive numbers. So if you're going to 0 through positive numbers, that would be a plus infinity. But in either case, this is just showing you that this is a limit of the form 0 times infinity, either plus or minus. So just so we can see that we need to do something more. And what are we gonna do in here? In order to apply L'Hopital, when you encounter a limit like this, 0 times infinity, what you have to do is you're gonna rewrite one of the functions as its reciprocal in the denominator. That way, it's going to be either 0 over 0 or infinity over infinity. In this case, cosecant is a function that is defined as a quotient, as 1 over sine. So what we can do, and it doesn't matter if it's from the right or the left, we can write that the limit is equal to this particular limit. Instead of cosecant, we're going to write 1 over sine. This is the step of transforming one of the functions in the product as something in a denominator, so that now you have a fraction. This is of the form 0 over 0 now, which means L'Hopital can be applied. And what does L'Hopital give you? Well, when we differentiate these functions, you don't get just cosine of 3x and cosine of 7x. Not just that, but because of the chain rule, you need to multiply these guys by the derivative of the inner functions, 3x and 7x, giving you this 3 and 7. Don't forget the chain rule. We see many examples of this kind of thing already, where you have a function applied to a number of the form ax, where a is a constant, like the number 3 here. That a always appears in the end as because of chain rule as a constant multiplying. But okay, now this is a limit where it's possible to plug in x equals 0. Cosine of 0 is 1. So 1 times 3 divided by 1 times 7, that is just 3 over 7. So yeah, this is a limit that we already knew how to do before. Whenever you encountered something like this, our trick earlier would be to divide and multiply by both 3x and 7x, so that you can apply the fundamental limit involving the sine function. While L'Hopital, we're just showing you here that L'Hopital also helps you with this. Moving on, a little bit of a different problem here. What is wrong with the following calculation? So imagine a student was trying to compute this limit. X is going to 2, and they apply L'Hopital, plugging in derivatives. The derivative of x squared minus 4x is 2x minus 4. The derivative of x squared minus 4 is just 2x. And now if you plug in x equals 2 in here, the numerator becomes 4 minus 4, which is 0. Denominator becomes 4. 0 over 4 is 0. But this limit is not actually equal to 0. And there is something wrong. What is wrong? Well, it is right here. You cannot apply L'Hopital to all quotients like the student just did here. You can only do that if the original limit was an indeterminate form, 0 over 0 or infinity over infinity. So what is actually wrong? Well, this original limit is not of those forms, because what happens when you try to plug in 2? In the numerator, you have a 4 minus 8 plus 3. So that's minus 1. If I'm not mistaken, yeah. And the denominator becomes 0. Yeah, just double checking. So this is of the form non-zero number divided by 0. This is a limit that gives you either plus or minus infinity or DNE, depending on which side you're coming from. But what the point is that this is not indeterminate form. So L'Hopital LH cannot be used. And technically, we have now already answered the problem. What is wrong? This is what's wrong. You cannot apply L'Hopital here. If they had also asked what is the limit, well, we know how to do this one. I'm not going to do it. But essentially, what you have to do is analyze it from the left and the right to see what's changing sign. In fact, there will be either a plus or minus infinity, depending on which side you're coming from, which means the limit itself does not exist. But yeah, let's not do that. So just be careful when you apply L'Hopital blindly. You need to first verify that you actually can do it. Another one here, also a different type of problem. Consider this limit. First of all, verify that L'Hopital is not helpful, even though it can be applied. So we're going to do that. This is a little annoying to verify, to see that it's indeterminate form, but it is. Let's try that quickly. X is going to 0 from the right. The limit of the numerator function, that's the one that you have to be careful when analyzing. What is happening here? So if x is going to 0 from the right side, this expression 1 over x, well, you're dividing by 0, so it is going to either plus or minus infinity. Because x is positive, that's a plus infinity. But then there's an extra minus sign in front of that. That's this minus here. And then finally, e to minus infinity is 0. This is really, if you want to write this formally, the limit of e to the minus u as u goes to infinity is 0. You can think about the graph of the exponential function, which looks like this, to remind yourself about why this is true. Is if you're taking x to minus infinity, you see that the graph is converging towards 0. Okay, so it is a 0 in the top. It is a 0 also in the bottom. That's just x, that's easy. So it is 0 over 0. We can apply L'Hopital. Item A is asking us to verify that it's actually not going to be helpful. Let's see why. So the limit as you approach 0 from the right, e to the minus 1 over x. Let's use L'Hopital. What is that going to give us? Okay, denominator is the easy one to find a derivative. That's just 1. But the numerator is going to require the chain rule. The exponential function, when you differentiate it, it's just given itself, e to the minus 1 over x. But then you need to multiply that by the derivative of minus 1 over x, which is plus 1 over x squared by power rule. So what do you get? You're going to get this limit. You still have this exponential, e to the minus 1 over x, and then you have an x squared in the denominator now. Which, well, it looks more complicated than the original limit, right? The original just did not have the square here. And it was just x, and now it is x squared. So this is not helpful for you. Okay. Yes, this is correct. Sorry, I was double checking my work. That's what they meant in item A. This is not helpful. You could try to apply L'Hopital again, because this is again 0 over 0. But if you do that, you're going to see that you just keep getting larger and larger powers in the denominator. So we can answer item A like right here. What is this limit? We don't know. It was not helpful. Even though it's true, we don't know what L'Hopital, by using L'Hopital, we don't get an answer here. Now, item B is saying verify that L'Hopital helps if you rewrite the function in this form. First of all, let's try to understand what's going on in this form. Basically, the exponential function, which was with a negative exponent, we brought it downstairs in the denominator with the positive exponent. That's going to be the same thing. And then similarly with the x. Instead of having x in the denominator, we have 1 over x in the numerator. Also the reciprocal of that. So the function in this form is the same function. 1 over x divided by e to the 1 over x. This is the limit that we are now trying to find. It is the same function. Okay, how do we do this limit? Can you do L'Hopital? Yes, you can. For the same reason as before, but now it's infinity over infinity. If x is going to 0 plus, 1 over x goes to infinity. And then here, this 1 over x also goes to infinity. And then e to the infinity is also infinity. So we know that we can do L'Hopital. And what does that give you? So let's find the derivatives. Derivative of 1 over x is minus 1 over x squared. Derivative of the exponential is the exponential itself times minus 1 over x squared by chain rule. Okay, we can now cancel the minus 1 over x squared. Let those go away. It's the same thing in numerator and denominator. So you are just left with limit x goes to 0 plus 1 over e to the 1 over x. This is now one that we know. It's 1 over infinity. We can say 1 over e to the infinity. Again, just reasoning just like before. 1 over x is going to infinity. E to the infinity is infinity. 1 over infinity is 0. So that's the answer. All right, so what is this problem showing us? It's showing us that sometimes, even though you can apply L'Hopital, maybe it's not going to help. Maybe you need to simplify, modify the function somehow. This was a slightly hard modification to find. Usually it's not going to be this difficult. Usually it's a simplification. But you should always try to simplify as much as possible before you try to apply L'Hopital. Next one. We have a limit at infinity now instead of at a number. Compute this, and we'll read the note later, the meaning of this computation. Let's see what happens to this limit. So x is going to infinity. You have e to the x and x cubed. Both are going to infinity. So you can do L'Hopital. Let's do L'Hopital. Derivatives. Derivative of e to the x is e to the x. Derivative of x cubed is 3x squared. This was helpful because we decreased the degree here. It was 3, now it's 2. The function is a little bit simpler. We just don't see how much, don't immediately see an answer yet. This is still infinity over infinity if you try to think about what's happening. Both e to the x and x squared are going to infinity. So you can do L'Hopital again. We've seen examples of this where L'Hopital is used more than once. Now it becomes e to the x over 6x, taking the derivatives of those two functions. This is still infinity over infinity. We can do L'Hopital again. But we know that we're going in the right direction because the function is getting simpler. And this time, 6x becomes 6. This is no longer indeterminate. This is infinity over 6. Infinity over positive number, that's also infinity. That's the answer to this limit. And okay, so this was the answer, computed, we computed. What I wanted to point out is this note here. This limit can be regarded as an attempt to compare the relative sizes of the functions, e to the x and x cubed, as x becomes large. So in other words, when you take large numbers, so when x goes to infinity, the fraction of the exponential divided by x cubed goes to infinity. It becomes large. And the only way that that can happen is if the function in the top is larger than the function at the bottom. Not just larger, but getting larger and larger in comparison. So what this computation here is showing is that the exponential function grows much more than the x cubed function, or in fact, any polynomial function. It's a measure of how they compare to each other. And L'Hopital gave us how that goes. So basically, even though both functions are going to infinity, here's x cubed, here's the exponential starts growing much faster. Okay, so the next problem is gonna, instead of giving us the limit, it's gonna ask us what happens when you want to compare two functions. So when x is large enough, which function becomes larger, x cubed or 1.1 to the x? And the answer is going to be the second one. It's always the exponential function. It beats any polynomial. It grows faster than any polynomial. But how do we see that? We try to compare them. We create a limit with x going to infinity because, let me color code this, because they said when x is large enough. So we know that we want to be taking x to infinity, large. All right, and then we try to compare one function to the other. It doesn't matter which order we do it, just one over the other. Then whatever answer we find from here, we're gonna then analyze it, what it means. So let's try to compute this limit. This is infinity over infinity. X cubed goes to infinity, that's clear. 1.1 to the x also goes to infinity because 1.1 is larger than 1. An exponential function with the base larger than 1 always looks like this. So like a to the x for a larger than 1. If a is smaller than 1, it would be the contrary. So this is one of the graphs that we should remember, and it justifies this infinity. So we can do L'Hopital. Let's do it. The derivative of x cubed is 3x squared. What is the derivative of 1.1 to the x? You don't do the power rule here. Let me write it and erase it. It's not x 1.1 to the x minus 1. I hope you realize that's not what it is, because this is called exponential function. The variable is in the exponent. When you have that, the rule is the function itself times the ln of the base, which is 1.1. So just like the with the exponential function e to the x, ln of e would have been just 1, right? So this is the derivative. All right, ln of 1.1 is just some positive number because it's larger than 1. And this is still a limit going to infinity over infinity. Again, because of the exponential and the x squared. So we're going to do L'Hopital again. And you see where this is going. L'Hopital is going to be applied 3 times, just like before. 6x divided by, what is the derivative downstairs? Well, you don't need a product rule here, even though it's a product of 2 terms. One of them is just a constant. That constant just remains there. And you really just want to differentiate the exponential part. And that's the one that we just did. 1.1 x to the x times ln of 1.1. So the derivative just brought you an extra factor of ln of 1.1. That's what happened. All right, but this is still infinity over infinity. We can do L'Hopital once more. And we're going to get, this time, 6 divided by. Similarly, the 2 factors of ln of 1.1 still remain there. And you're going to get another one from another derivative. So I'm going to write it cubed. ln of 1.1 cubed. And then the 1.1x. I just took a derivative, that's all. Now we are in a good shape here. This time 6 goes to 6, and the 1.1 to the x goes to infinity. This number in front of it is just some positive number, so it doesn't affect anything. But finally, 6 over infinity is 0. This is the answer to the limit. Now remember why we were doing that. We wanted to compare the two functions. What do you think is happening now then? Which function becomes larger? Well, when we divided them in this order, the polynomial by the exponential, we found a 0. So that means that the numerator is very small compared to the denominator. That's the only way that you can get a 0 in the fraction, a limit of 0. So we get our answer here that x cubed is, you can write it like this, small compared to 1.1 to the x. This is the answer. You could have chosen to compare them in the reciprocal order, 1.1 to the x divided by x cubed. You would find the answer infinity, and the conclusion would be the same. Still that, well, if the reverse fraction is going to infinity, that means the numerator is larger than the denominator, which is the same conclusion as here. So, all right, this is how we can compare functions in a limit. Maybe I'm gonna leave this one as an exercise. This is just L'Hopital once again, but several times. Let me at least verify that we can do L'Hopital. X is going to 0. So you see that 1 minus 0 inside of ln is just 1. ln of 1 is 0. And then everything else here contains a factor of x. Those are all going to 0. So we know this is 0 over 0. We know that you can do L'Hopital. So keep going. But at least I'm going to point you to this remark. What is the derivative of ln of 1 minus x? Don't say that it's just 1 over 1 minus x. That would be incorrect. This is the derivative of the ln function evaluated at the function 1 minus x. But this is the inner function in the chain rule. You need to multiply this by its derivative, which is minus 1. That's the derivative. So keep this in mind, but try to do this yourself. I'm going to be moving on. We have another topic to cover today, antiderivatives. So, all right, this was done in another lecture. Just as a quick reminder, if you have some continuous function little f, we denote by this symbol here, integral of little f dx, a antiderivative and antiderivative of the function little f. By definition, what is that? It's a function big F whose derivative is little f. So antiderivative is the reverse of derivative. And we've also seen that if your domain is an interval, then once you find one antiderivative, you can get all the others by adding a c. Now, what we are going to do, okay, so I have one quick example before we do the initial value problems. This one is just asking us to compute an antiderivative. Let's see what happens here. The variable of integration is called t instead of x. And we have a quotient. I told you that there are no general rules for quotients or products. You cannot take the antiderivative individually in each piece. You cannot do that. That would be hard to do for us right now. We don't even know how to get that. Like a function whose derivative is, for example, this first term. That's kind of complicated to think about. But instead, what we have to do is simplify everything. In this case, you have a sum or difference in the numerator. Meanwhile, the denominator is just one term. You can split the fraction like this. So 2t e to the 2t divided by t e to the e to the t minus second term divided by the same denominator. So by splitting it this way, we can see the simplifications. In the first term, the t's go away, and e to the 2t divided by e to the t, you're going to subtract the exponents. 2t minus t just leaves you an exponent of t. So this is 2e to the t minus the e to the t's in the second term go away. This is just 6 over t. This is the simplification, and now this function became a sum or difference in this case, of two functions whose antiderivatives we know. Namely, the antiderivative of e to the t would be e to the t itself, a function whose derivative is e to the t. And there's a factor of 2 in front. I'm leaving that 2. Now for the second part, there is a factor of minus 6. Let's leave that. And now what is a function whose derivative is 1 over t? Well, remember, it's not just ln of t. This is what it is if t is positive, but because we don't know in this integral, we have to write absolute value. When t is negative, that function also gives you 1 over t after differentiating. So we have to put this absolute value there. This is one antiderivative. And finally, what the symbol actually means is all of the antiderivatives. You have to include a plus c. That's the answer. And now I can actually go to a problem that's about what I had mentioned before, initial value problems. Just as a quick reminder, what does this mean? Well, it means exactly what you see on screen here. We are trying to find the function f with these two properties here. That's what they mean by solve the initial value problem. It means find the f. So on the one hand, the derivative of f must be this particular function, 5e to the x plus 2. And on the other hand, the value of the function at the number 0 must be 0. This is called the initial condition. So what do? First, you look at the differential equation, the first one. If the derivative of this function is 5e to the x plus 2, that means that the function itself must be the integral of that, or antiderivative of that. This is the first step. We need to find this integral. That's a very easy one to do. 5e to the x, well, the antiderivative is 5e to the x. 2, what about the number 2 here? Antiderivative of a constant, it's just 2x. Because when you differentiate 2x, you find 2. And don't forget your plus c. So from the first equation, this is what we get for f. Now what we have to do, f of 0 is 0. So on the one hand, I'm going to color code like this. 0, the value, is equal to f of 0, the argument. So we are going to be plugging in zero the argument into the function f. Those should be the blue zeros here, the argument x equals 0 plugged into the f that we just found. Because this is an equation that allows you to find c. Look at this equation now. It is 0 equals, this is 5. 2 times 0 is 0. And then plus c. This last part of the equation is here, plus c. So you see here, c must be minus 5. After you found c, remember that the answer to the problem is the function itself. F of x must be the function 5 e to the x plus 2x minus 5. I'm looking at the f that we found initially and writing it with the value of c that we just found. This is your answer. All right. So I'm going to do one more of like this. Solve the initial value problem. Very similar to the last one. Let's see how this works. In this problem, we're going to need to integrate sine and cosine. So you probably should remember this little trick where you draw the unit circle. You draw either sine or minus sine and either cosine or minus cosine in the correct places. Integrals go counterclockwise. Integration. So for example, the integral of cosine is sine. All right, so this is helpful for you to remember how to integrate trig functions where you also have pluses and minuses in front. All right, let's do this. F of x. F prime is given as 3 sine x minus 2 cosine x. So we need to find the antiderivative of this. Write this number 3, the constant, and then find the antiderivative of sine. What is that? Look in the circle, it's minus cosine. Now, you can think about this any way you want. Maybe the 2 is your constant, or maybe the minus 2 is your constant. That doesn't matter. And like the minus could have been considered as part of the cosine or part of the minus 2. It's probably easier to leave it as part of the minus 2. And then you need to find the derivative of cosine, antiderivative of cosine. What is that? Look here, it's sine. The function whose derivative is cosine. So plus c, let me just rewrite this to clean up. Minus 3 cosine minus 2 sine plus c. That's your f of x, but we don't know c yet. C is going to be found from the initial condition. At the number 3 pi over 4, the value of the function must be pi. So pi, the value, is f of 3 pi over 4. Plugging in 3 pi over 4 into the function. This is what you get. We're going to need to remember our trig values. 3 pi over 4 is the 135-degree angle, second quadrant. The sines and cosines are root 2 over 2, but the sine is positive and the cosine is negative. So here, minus 3 times minus root 2 over 2, minus 2 times plus root 2 over 2, plus c. All of this must be equal to pi, this pi right here. So now you just solve for, yes, solve for c. You have a 3 times root 2 over 2 minus, let's say 2 times root 2 over 2 plus c. So that's pi equals root 2 over 2 plus c. C is equal to pi minus root 2 over 2. Having the value of c, you know what your function must be. Go back to the formula for f of x. It's right here. Minus 3 cosine minus 2 sine plus c. So plus, here's the value of c that we just found. Pi minus root 2 over 2. That's the function. My last slide now. is going to be kind of an applied problems involving initial value problems. I mean, right now they're just abstract things for us. We don't know much about where they can show up. This is the prototypical place where that kind of thing shows up, motion problems. So we should be aware of these, of the language that you see in this. When you have a function, usually a function of t, where t is time, and it represents position at time t, then the derivative represents velocity. We know this already because we know that the derivative means instantaneous rate of change, right? The rate of change of position is what we call velocity, measured, for example, in miles per hour. Well, and then if you take two derivatives, that you get acceleration. By definition, that is what acceleration is: instantaneous rate of change of velocity. So what is the reasoning here? If you know the position function to a certain variable, a certain particle, sorry, then we can find the velocity taking a derivative. This should be very intuitive to think about. If you know the position of something at all points, you can find its velocity as well. It's perfectly well defined. But the process going the other way, if you know the velocity and you want the position, well, you can find it almost completely. You can determine the position. You're going to need an antiderivative to go from velocity to position, as long as you also know the value at any specific instant, initial value. So think about it this way. Maybe I tell you the velocity of a particle is 5 miles per hour or whatever, 5 every time, so constant velocity. And I ask you, what is the position? Well, you don't know yet because you don't know where it started. All you know is that it's going with a speed of 5, I guess, this direction. But where did it start? You don't know yet. So as long as you're given one initial value, then you're able to find the position. This is exactly the type of thing that we've been doing with initial value problems. Going back to the previous slide, the process of taking an antiderivative, you can think about it this way. It it almost completely determines the function, but there's one unknown, 1 plus c, that you, in order to find that, you just need the value of the original function at one specific value or point. All right, so here's the example that I wanted to give, a very simple one. A car moves with a constant acceleration function, a of t equals 2. First item is find the velocity v of t, given that the velocity v of 1 was minus 5. So let's do this. The function acceleration is always v prime, velocity prime. We should know this. We should always remember this. Acceleration is the rate of change of velocity. So they told us that this is the 5 function. Acceleration is constant equals to 5, and we want to find v. So we're going to be writing an initial value problem for the function v. On the one hand, v prime, which is acceleration, is always 5. And on the other hand, the value at 1 is minus 5. This is now an initial problem for v. With this, we can find v. So let's do that. If v prime is 5, then v must be integral of 5. The variable is called t in this problem. It's time. All right, so antiderivative of 5 is 5t plus c. Maybe I'm going to call it c1 because there will be another c later for the item b, right? You can call your constants whatever you want. So c1. This is the antiderivative. How do we find c1? We know that v of 1 on the one hand is minus 5, and on the other hand, plugging in 1 into the formula that we just found. 5 times 1 plus c1. So this equation is minus 5 equals 5 plus c1. c1 is equal to minus 10. So you found your velocity position, velocity function, 5t minus 10. This is what item A was asking about, find the velocity function. B is going to be the same thing for position. Now find the position function, b of t. given that the position at time 0 was 10. Okay, so we have the velocity. What is the relationship between position and velocity? Velocity is position prime. Rate of change of position is velocity. Now we do know what velocity is already. We know it's 5t minus 10. So now we're going to write an initial value problem for p. P prime is the velocity function that we just found, and p of the instant 0 was given in the problem as minus 10, or sorry, plus 10. This 10 right here. So solve this problem for p now. Let's integrate 5t minus 10 dt. Integral of 5t is, remember the power rule. How do you find, well, leave the 5 outside. Now t is the same as t to the 1. How do you find the derivative, the antiderivative of that? Add 1 to the exponent and also divide by that same thing. So it's going to be t squared over 2. The same rule gives you the antiderivative of a constant. Minus 10 would be minus 10 times t. Plus, let's call this one c2 now. So this is 5 over 2 t squared minus 10t plus c2. How do we find c2? Use the initial value condition. 10 is p of 0, which is, now plug in 0 for t is very easy, because the t squared and the t are just 0. So this just leaves you c2 equals 10. Nothing to solve here. So you find the position function. 5 over 2t squared minus 10t plus c2, which is plus 10. Okay, so this was just to showcase that what we have mentioned above here. When you know a function which is a derivative, which is a rate of change, like acceleration, you can find the velocity up to some constant, and you need some initial value to determine that constant. This is what initial value problems are all about. And we're going to find them mostly in this language, the language of motion problems. You have a function for position or height or something like that. So just remember these relationships between acceleration and velocity. So acceleration is actually position double prime, if you think about it.